Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through the hidden geography of black holes. For now, imagine leaving Earth behind and moving outward through the quiet dark between stars. Ahead of you are not only empty regions where light disappears, but real places in the universe. The center of the Milky Way, the giant galaxy Messier 87, the Cygnus constellation, the detectors of LIGO, the bright hearts of quasars, and the dense star clusters where hidden masses may be waiting. The journey is not a fall into one single darkness. It is a tour of many discoveries. Some black holes are the collapsed remains of massive stars. Some sit at the centers of galaxies. Some tear gas from companions. Some merge in complete darkness and announce themselves only by shaking space-time. Some may exist as candidates, still waiting for stronger evidence. The first discovery is simple, and it corrects one of the most common images. A black hole is not a cosmic drain pulling everything in from across space. From far away, its gravity behaves like the gravity of any other object with the same mass. The strangeness begins when mass is packed into a region so small that escape paths eventually close. Imagine approaching a black hole from a safe distance. You might expect to see a wall, a shell, or a solid edge. But the event horizon is not made of matter. It has no crust. It is not a place where a ship would hit a physical boundary. The event horizon is a boundary in causality. Outside it, light can still move outward and carry information to the wider universe. Inside it, every possible future path points deeper inward. Locally, light still travels at light speed. Nothing strange happens to the light itself. What changes is the geometry of space-time around it. This is why black holes are less like objects sitting in space and more like regions where space and time have been shaped beyond ordinary escape. Now move far away from the horizon and imagine replacing the sun with a black hole of exactly the same mass. Earth would not suddenly spiral inward. Its orbit would remain almost the same because gravity at Earth's distance depends mostly on mass and distance, not on whether that mass is shining, collapsed, or hidden. The disaster would be the loss of sunlight, not magical suction. This correction matters because it lets black holes become scientific objects again. They are not monsters reaching across the galaxy. They are extreme gravitational systems. The danger appears when something comes close enough for escape paths to narrow. Far away, a black hole can be orbited. Nearby, it can bend light, heat gas, stretch matter, and finally close the road outward. For a non-rotating black hole, the event horizon is described by the Schwarzschild radius. The idea is surprisingly clean. More mass means a larger horizon. If the mass doubles, the horizon radius doubles. If the sun could somehow be compressed into a black hole without changing its mass, the horizon would be only a few kilometers across. If Earth were compressed into a black hole, the horizon would be roughly the size of a small coin. These examples are not formation stories. The Sun and Earth do not naturally become black holes this way. They are scale lessons. A black hole forms when enough mass is confined within its own escape boundary. The object is not defined by darkness alone. It is defined by compactness. Now travel to a blue-white star far more massive than the Sun. From the outside, it shines with power. Inside, gravity and pressure are locked in a temporary balance. Gravity pulls inward. Fusion in the core creates pressure that pushes outward. The largest stars spend their fuel quickly. Hydrogen fusion gives way to helium, then to heavier burning stages if the star is massive enough. Carbon, neon, oxygen, and silicon can burn in layered shells around the core. The structure is sometimes compared to an onion, but it is not quiet. It is heat, pressure, radiation, and nuclear transformation held together by gravity. The more massive the star, the shorter the life. What looks majestic from outside may be racing toward collapse. The final turning point comes when the core builds iron group elements. For much of a massive star's life, fusion releases energy. That energy helps support the star against gravity. Iron changes the bargain. Fusing iron into heavier elements does not release useful support in the same way. It requires energy. Once an iron-rich core grows beyond what pressure can hold, the center can no longer answer gravity. Collapse begins. Matter falls inward at tremendous speed. Electrons and protons are forced together, producing neutrons and neutrinos. The outer layers may explode as a supernova. The core may become a neutron star. But if enough mass remains, even neutron pressure cannot halt the collapse. The horizon forms, and the remnant becomes a black hole. Pause beside a neutron star before moving onward. It is already extreme, a city-sized remnant containing more mass than the Sun. It has a surface. It can emit light. It can have a crust, a magnetic field, and a measurable spin. A black hole is different. It is what happens when no known pressure leaves a stable surface outside the horizon. This distinction keeps the science clean. A neutron star is not a black hole that has not finished becoming dark. It is a different kind of compact object. The boundary between the two depends on mass, equation of state, and the physics of dense matter. That boundary is still studied, but the observational difference is clear. One can have a surface, the other hides whatever crossed inside. Now turn toward the constellation Cygnus. Cygnus X. One became one of the most famous black hole candidates because it showed how an invisible object can reveal itself through a companion star. In a system like this, a massive visible star orbits an unseen compact companion. Gas can be pulled away, heated in an accretion flow, and made to shine in X-rays. The visible star's motion gives a way to estimate the hidden mass. If the unseen companion is too massive and compact to be a neutron star, a black hole becomes the strongest explanation. Cygnus 1 matters because it connects black holes to real astronomy. The evidence is not a picture of a hole. It is a pattern of motion, mass, radiation, and compactness. Not every black hole glows. Imagine a stellar mass black hole drifting through the Milky Way with no companion star, no disk, and no gas cloud nearby. It may be almost impossible to see directly. This quietness is not a contradiction. The horizon itself does not shine like an ordinary surface. A black hole becomes bright mainly when surrounding matter is available. Without nearby material, it may reveal itself only through gravity. That gravity can still matter. A passing black hole can bend the light of a background star through gravitational microlensing. It can perturb nearby objects. It can carry the hidden record of a dead star through the galaxy. Darkness in this case is not emptiness. It is the absence of an easy messenger. Now move inward through our own galaxy toward Sagittarius, a star. It lies about 27,000 light-years away, behind dust and crowded stars toward the constellation Sagittarius. We cannot visit it, but we can measure its neighborhood. For decades, astronomers tracked stars near the galactic center. Some of those stars sweep around an unseen central mass at high speeds. Their orbits show that millions of solar masses are packed into a very small region. This is one of the most powerful destination anchors in black hole astronomy. Sagittarius. A star is not an abstract idea from a textbook. It is the dark center of the galaxy we live in, revealed by the motion of real stars moving through the innermost Milky Way. One star near Sagittarius. A star, often called S2, has been especially valuable. It follows an elongated orbit around the invisible central mass. By watching it over years, astronomers can test gravity close to the supermassive black hole. When S2 passes near its closest approach, its light is affected by the strong gravitational field and by its high speed. Observations of this orbit have helped confirm that the object at the center of the Milky Way behaves as general relativity predicts for a compact, massive object. This gives the listener a real scene, not a vague center, but a star moving like a bright marker around a hidden gravitational focus. The black hole is known through choreography. Now leave the Milky Way and travel to the giant elliptical galaxy, Messier 87. At its center is Messier 87 star, a supermassive black hole with a mass measured in billions of suns. This is a very different destination from Sagittarius A star. The Milky Way's central black hole is massive by human standards, but modest compared with the engine inside Messier 87. A larger horizon changes the scale of the surrounding system. It can support a vast accretion environment and power a jet that reaches far beyond the central region of the galaxy. Messier 87 teaches that black holes are not only endpoints of stellar death. At galactic centers, they can become engines in the evolution of enormous cosmic structures. In 2019, the Event Horizon Telescope released the famous image of Messier 87 star. It showed a bright ring around a dark central region. The image was often described as a black hole photograph, but careful language matters. The picture does not show a solid surface. It shows radio emission from hot material near the black hole, shaped by extreme gravity. The dark central region is the black hole shadow, related to the event horizon but not identical to the horizon's exact edge. The image matters because it made curved space-time visible in a new way. Light near the black hole bends, circles, brightens, fades, or fails to reach us. The darkness has a shape because gravity controls the paths of photons. The Event Horizon Telescope is not one telescope. It is a network of radio observatories spread across Earth. By combining signals from distant sites, scientists create the resolving power of a planet-sized instrument. This technique, called very long baseline interferometry, is necessary because black hole shadows appear incredibly tiny on the sky. Even supermassive black holes are small targets at astronomical distances. The destination here is not only Messier 87, or the Milky Way. It is Earth itself, turned into a measuring device. Dishes in different locations observe together, and the planet becomes part of the instrument. A black hole is so distant and compact that seeing its shadow requires a telescope as wide as the world. The Event Horizon Telescope later released an image of Sagittarius A star. It is much closer than Messier 87 star, but it is also much smaller in mass. That creates a different challenge. The gas near Sagittarius A star changes on short timescales. During an observation, the emission can vary, making the target harder to reconstruct. Messier 87 star is farther away, but much larger, so its surrounding pattern changes more slowly. This is a useful correction. Closer does not always mean easier. In black hole imaging, distance, mass, angular size, brightness, and variability all matter. Sagittarius. A star is our galaxy's central black hole, but photographing its shadow is like trying to image a storm that changes while the camera is still open. Now imagine a black hole with gas falling toward it. The gas usually does not drop straight in. It has sideways motion, so it forms a rotating accretion disk. The disk is not a solid plate. It is hot plasma, turbulence, radiation, and magnetic fields. Inner regions orbit faster than outer regions. Energy is converted into heat and light before the material crosses the horizon. This explains one of the most beautiful contradictions in astronomy. Some of the brightest environments in the universe are powered by objects whose defining feature is that light cannot escape from inside them. The horizon is dark, but the surrounding matter can blaze. A black hole is often discovered not by its darkness, but by the light it forces other material to release. Travel now to the early universe, where some young galaxies host active supermassive black holes. When gas feeds the central black hole rapidly, the accretion flow can shine with extraordinary power. These objects are called quasars. A quasar is not a black hole glowing like a star. It is the environment around a feeding supermassive black hole radiating across immense distances. Some quasars are so bright that they can be seen from billions of light years away. This gives black holes a new role in the story. They are not only hidden endpoints, they can become engines visible across cosmic time. A quasar is a lighthouse from a young galaxy, but its lamp is not a surface. It is gravitational energy released by infalling matter before the final crossing. Look above and below an accretion disk around an active black hole. In some systems, narrow jets extend outward at enormous speeds. They can reach thousands or even millions of light years from the center of a galaxy. This scene can create a misconception. The jets are not matter escaping from inside the event horizon. Once material crosses the horizon, it cannot send a signal back out. Jets are launched from outside the horizon in the environment of rotating plasma, magnetic fields, and black hole spin. A jet is therefore not an exception to black hole darkness. It is evidence that the surroundings are violently organized. The black hole hides what crosses inward, while magnetic fields and infalling matter can drive energy outward before the crossing. Messier 87 is famous not only for its shadow image, but also for its enormous jet. The jet extends from the central region of the galaxy and can be observed across different wavelengths. This gives the listener a recognizable destination with a visible structure. At the center is a supermassive black hole. Around it, gas and magnetic fields form an active environment. From that environment, a jet reaches into intergalactic space. The scale is almost difficult to hold. A horizon that is tiny compared with its host galaxy can be connected to structures stretching across vast distances. The black hole is not physically large compared with the whole galaxy, but it can help organize energy on a galactic scale. In galaxy clusters and large galaxies, active black holes can heat surrounding gas. Jets and outflows can inflate bubbles, stir the environment, and affect how easily gas cools into new stars. This is called feedback. It is one of the ways a central black hole can influence a galaxy much larger than itself. The black hole does not reach out by gravity alone and sculpt every star. Instead, energy from accretion and jets interacts with the surrounding gas. The key discovery is proportional surprise. A central black hole may contain a tiny fraction of a galaxy's total mass, yet its feeding episodes can change the conditions for future star formation. The dark center can help decide how bright the galaxy becomes later. Now imagine a star wandering too close to a massive black hole. The side of the star nearer the black hole feels stronger gravity than the far side. If the difference becomes extreme enough, the star can be stretched and torn apart. This is a tidal disruption event. Some of the stellar material may fall inward and heat up. Some may be thrown away. The black hole itself remains dark, but the destruction creates a flare that telescopes can observe. This is not ordinary suction. It is differential gravity. The star is not pulled apart because the black hole is hungry in a human sense. It is pulled apart because different parts of the same star are forced onto different paths. Gravity becomes a sculptor of catastrophe. The word spaghettification is memorable, but the physics behind it is more precise. It refers to tidal stretching. Your feet, if pointed toward a compact black hole, would be pulled more strongly than your head. At the same time, sideways directions can be squeezed. Near a small stellar mass black hole, tidal differences near the horizon can be extreme. Near a supermassive black hole, the horizon is much larger, and tidal differences at the horizon can be gentler. That does not make the environment safe, but it changes where the stretching becomes lethal. The lesson is subtle. Gravity's strength and gravity's variation across distance are related, but not identical. What tears an object apart is not only gravity, it is the difference in gravity from one side to the other. It sounds natural to assume a larger black hole must always be more dangerous at its horizon. But size changes the experience. A stellar mass black hole has a much smaller horizon, so tidal forces can change dramatically across short distances. A supermassive black hole has a much larger horizon. At the boundary itself, tidal differences can be less severe for a large enough black hole. An observer crossing in a purely idealized case might not feel a dramatic surface-like event at the horizon. The danger remains absolute in another sense. After crossing, no return signal is possible. But the physical sensation of crossing depends on mass. This is one of the reasons black holes keep correcting intuition. Bigger does not always mean harsher at the edge. Now move to a binary system, where two black holes orbit a shared center of mass. If they are far apart, the orbit can last a long time. But as they emit gravitational waves, they lose orbital energy. The orbit tightens. The black holes circle faster. The gravitational wave signal rises in frequency and strength. Finally, the horizons merge, and the new black hole settles through a phase called ring down. This is a new kind of destination, not a place lit by stars, but an event written into space-time itself. Two dark objects can collide without a visible flash and still produce one of the most energetic events in the universe. The announcement is not light. It is geometry changing. In 2015, LIGO made the first direct detection of gravitational waves from a merging pair of black holes. The signal was tiny by the time it reached Earth, a stretching and squeezing far smaller than an atom across the detector arms. The discovery opened gravitational wave astronomy. Black holes that might have been invisible to telescopes could now be detected through their motion. The waveform carried information about masses, spin, in spiral, merger, and final ring down. This discovery gives the episode another recognizable place. The long detector arms on Earth, measuring changes in distance as ripples pass through. The black holes merged far away. The evidence arrived as a whisper in the shape of space. LIGO is not alone. Virgo in Europe and Kagra in Japan add more listening points to the gravitational wave network. Multiple detectors help confirm signals and improve estimates of where they came from in the sky. This matters because a single detector cannot easily locate a source. With several detectors, the timing and shape of the signal can be compared. The network becomes a gravitational wave observatory spread across Earth. Again, the listener moves between destinations. Not only distant black holes, but human-built instruments on the planet below. Black hole astronomy is not just looking upward. It is also building machines sensitive enough to feel space-time move. Before gravitational wave detections, many known black hole candidates came from systems with light, X-ray binaries, active galactic nuclei, or stars orbiting unseen masses. Gravitational waves revealed black holes that do not need to be bright. Two black holes can merge in darkness. If there is little surrounding gas, there may be no optical flare, no X-ray burst, and no glowing disk. Yet the merger still radiates gravitational waves. This changes the population map. We no longer depend only on black holes that interact with matter. We can detect some that interact mainly through gravity. The universe becomes less biased toward the luminous. It begins to include dark systems that announce themselves by motion alone. Between stellar mass black holes and supermassive black holes lies a difficult category: intermediate mass black holes. These would contain hundreds to tens of thousands of solar masses, perhaps more, depending on the definition used. They are hard to find because they may not feed brightly, and they are not as common or obvious as galactic center giants. Astronomers search for them in dense star clusters, unusual X-ray sources, stripped galactic nuclei, and gravitational wave events that suggest heavier objects. This is a strong place for caution. Intermediate mass black holes have candidates, but the population is still being built through evidence. They matter because they may help explain how supermassive black holes grew so large in the early universe. Imagine a dense globular cluster, a sphere of old stars orbiting in the halo of a galaxy. In such a crowded environment, stars and remnants can interact over long timescales. Heavy objects tend to sink toward the center through gravitational encounters. This makes globular clusters possible hunting grounds for intermediate mass black holes. If a hidden black hole sits at the center, it might affect stellar motions or produce faint accretion signatures. But the evidence is difficult. Dense clusters are complicated. Many smaller dark remnants can sometimes mimic some effects of a single larger object. The documentary's safe wording is not that every cluster hides a black hole. It is that dense clusters are natural laboratories where the search for the missing middle continues. Some quasars in the distant universe appear to host very massive black holes when the cosmos was still young. This creates a growth question. How did such large black holes form so early? Several ideas are studied. They may have grown from the remnants of early massive stars. They may have formed from heavier initial seeds, perhaps through direct collapse of gas under special conditions. They may have grown rapidly through accretion and mergers. The important point is not to pretend the answer is settled. The early growth of supermassive black holes remains an active research area. The discovery is the puzzle itself. The young universe already contained engines massive enough to shine as quasars across cosmic time. From outside, an isolated black hole can be described by a small set of properties: mass, spin, and electric charge. In realistic astrophysical settings, charge is usually expected to be negligible, leaving mass and spin as the main measurable traits. This simplicity is sometimes called the no-hair idea. It does not mean the black hole has no history. It means that many details of the material that formed it are not visible from outside the horizon. This is scientifically beautiful and unsettling. A collapsed star, a swallowed gas cloud, or a merger can leave behind an object whose external description is astonishingly simple. The universe preserves mass and angular momentum, but hides many details behind the causal boundary. Most astrophysical black holes are expected to spin. A rotating black hole is described by the Kerr solution rather than the simpler non-rotating picture. Spin changes the surrounding spacetime. It can create frame dragging where spacetime itself is dragged around the rotating object. Near a rotating black hole, orbits, disk behavior, and energy extraction can differ from the non-rotating case. This gives another discovery reset. The black hole is not only massive, it can rotate. That rotation matters for accretion disks, jets, and tests of general relativity. The horizon remains one way, but the region outside it becomes richer. A spinning black hole is not a static hole in darkness. It is a rotating geometry. Around a rotating black hole is a region called the ergosphere. Inside it, space-time is dragged so strongly that objects cannot remain still relative to distant stars. They must move with the rotation. The ergosphere is outside the event horizon, and that distinction matters. In principle, energy can be extracted from the rotation of a black hole through processes involving this region. In astrophysical settings, magnetic fields and plasma around spinning black holes are central to many jet models. The ergosphere is a powerful example of why black holes are not just dark circles. Their surroundings have structure. There are boundaries, regions, motions, and effects that must be kept separate. The horizon is one boundary. The ergosphere is another kind of region. Now step toward the quantum frontier. Stephen Hawking showed that black holes are expected to emit radiation due to quantum effects near the horizon. This radiation implies that black holes have temperature and entropy. For astrophysical black holes, Hawking radiation is extraordinarily faint, far colder than the cosmic microwave background for large black holes. We have not watched a stellar or supermassive black hole evaporate through Hawking radiation. This is where the script must be careful. Hawking radiation is a major result in theoretical physics, but observed black hole evaporation is not part of current astronomy. It belongs to the borderland where gravity, quantum theory, and thermodynamics meet. If black holes can evaporate, what happens to the information about what fell in? Quantum mechanics treats information in a particular way, while classical black hole horizons hide details from the outside universe. This creates the black hole information problem. It is not a simple mystery solved by saying the information disappears or the information escapes without qualification. Many ideas have been proposed involving quantum gravity, holography, entropy, and the deep relationship between space-time and information. For a sleep-friendly documentary, the safe path is to present the problem as a frontier. It is one of the reasons black holes matter beyond astronomy. They are laboratories for testing whether our deepest theories can fit together. Classical general relativity predicts that inside a black hole, collapse leads toward a singularity, a place where the theory reaches extreme limits. But the word must be handled carefully. We have not observed a singularity. It is hidden behind the horizon, and it may also signal that classical theory is incomplete under such conditions. Many physicists expect that a full theory of quantum gravity would change the description of the deepest interior. So, the documentary safe claim is not that scientists have photographed an infinite point. The safer claim is that general relativity predicts a breakdown like extreme inside black holes, and that the true physics of the innermost region remains unknown. Black holes often lead popular imagination toward wormholes. General relativity includes mathematical solutions that resemble bridges between regions of space-time. But no traversable wormhole has been observed. A responsible script can mention wormholes only as speculative and theoretical. They should not be presented as hidden tunnels inside real astrophysical black holes. The black holes we observe through stars, accretion, shadows, and gravitational waves are already extraordinary without turning them into science fiction doorways. This correction preserves wonder by sharpening it. The real universe does not need unsupported shortcuts. A black hole that bends light, shakes space-time, powers jets, and hides a horizon is already enough. White holes are sometimes described as time-reversed black holes, regions nothing can enter but from which matter or light might emerge. They appear in some mathematical discussions, but they have not been observed as astrophysical objects. This is another place for careful labeling. A white hole is not a confirmed companion to every black hole. It is not something telescopes have found in the sky. The useful role of white holes in the episode is conceptual. They show that equations can contain possibilities that nature may not realize. Mathematics can guide imagination, but observation decides what belongs to astronomy. Black holes cross that bridge into evidence. White holes have not. Primordial black holes, if they exist, would have formed in the early universe rather than from dying stars. They have been proposed in connection with early density fluctuations and sometimes discussed as possible contributors to dark matter. But they remain hypothetical. Searches and constraints continue across different mass ranges. Some possibilities have been narrowed, while others remain under investigation. This is a good example of active research without overclaiming. The episode can say that primordial black holes are scientifically interesting because they would connect black hole physics to the earliest universe. It should not say they have been found or that they explain dark matter. The discovery is the possibility and the search, not confirmation. Every black hole observation is also a test of gravity. Stellar orbits near Sagittarius. A star the shadow size of Messier 87 star, the ring down of black hole mergers, and the timing of gravitational wave signals all test whether general relativity continues to work in strong fields. So far, the theory has passed many demanding tests. That does not mean physicists stop looking. Black holes are exactly where small deviations might matter, because gravity is strong, space-time is curved, and ordinary intuition fails. This gives the journey a scientific spine. We are not only collecting strange objects, we are asking whether the rules that describe planets and light also survive near horizons and mergers. A black hole does not need to feed in order to reveal itself. If it passes in front of a background star from our point of view, its gravity can bend and magnify the star's light. This is gravitational microlensing. The black hole remains dark, but the background star briefly changes brightness or apparent position. Careful measurements can help estimate the lensing object's mass and motion. This discovery adds a quiet destination, a dark object crossing a line of sight in the galaxy. Nothing explodes, nothing glows. Yet the geometry of space itself becomes detectable. The black hole writes its presence into borrowed light. Some black holes may travel through the galaxy without bright companions. They could be remnants of supernovae, perhaps kicked by asymmetries in the explosion, or products of older stellar populations. The phrase rogue black hole sounds dramatic, but the science is calmer. It means an isolated or wandering black hole not easily seen through accretion. Detecting such objects is difficult, but microlensing and astrometric measurements offer possible routes. This kind of black hole makes the Milky Way feel less empty. Between the visible stars may be compact remnants moving silently through the dark. Most would be harmless at astronomical distances, but each one is a grave marker for a massive star. The word hole is useful, but misleading. A black hole is not an empty tunnel cut through space. It is a region with mass, gravity, spin in many cases, and a horizon that changes causal paths. If a star collapses into a black hole, the mass does not simply vanish. From outside, the gravitational influence remains. Nearby matter can orbit. Light can bend. Gas can heat. Detectors can measure waves from mergers. The hole is really about escape and information. It is a region from which future-directed signals cannot reach the outside universe. The name is memorable, but the physics is richer than a gap. A black hole is not a missing thing. It is an extreme presence. Around a non-rotating black hole, there is a region where light can, in an idealized sense, orbit. This is often called the photon sphere. The orbits are unstable, so a tiny change can send light outward or inward. The photon sphere is outside the event horizon. It helps shape the appearance of black hole shadows and lensing effects. Photons near this region can loop around the black hole before escaping, creating strange visual consequences. This gives the listener another boundary to keep separate. The event horizon is the point of no return. The photon sphere is where light paths can be dramatically bent and temporarily trapped. The black hole environment is layered with meaning. Near a black hole, gravitational time dilation becomes extreme. A clock deeper in the gravitational field can tick differently relative to a distant observer's clock. This does not mean time stops for the falling object in its own local experience. A falling observer's clock continues to tick normally for them. But from far away, signals from near the horizon become increasingly delayed and redshifted. The distinction is important. Science documentaries often flatten this into a simple phrase, but relativity depends on viewpoint. Time is measured along paths through spacetime. Near a black hole, different paths disagree in ways that are not psychological or poetic. They are physical. Imagine a beacon hovering near a black hole and sending light outward. As that light climbs away from the deep gravitational field, it loses energy. Its wavelength stretches and the light becomes redshifted. Near the horizon, this effect becomes extreme for distant observers. Signals can become dimmer, slower, and shifted toward longer wavelengths. This is one reason the horizon appears as a boundary to outside information. The image is gentle but profound. Light, trying to leave a deep gravitational well, is not tired in a human sense. It is following the geometry of space-time, and its measured energy changes between observers. Even light carries the memory of where it came from. A stellar mass black hole may be only tens of kilometers across at the horizon, yet it connects to the life cycle of massive stars. A supermassive black hole may have a horizon larger than a planetary orbit, yet it can affect the gas in a whole galaxy. This scale crossing is one reason black holes are so useful for long-form storytelling. They let the script move from a falling atom to a dying star, from an X-ray binary to a galaxy cluster, from a detector arm on Earth to a merger billions of light years away. The more the episode changes scale, the more it feels like travel. The black hole is the central idea, but each destination reveals a different face of gravity. Scientists sometimes ask whether some black hole candidates could be something else: exotic, compact objects, unusual stars, or new states of matter. This is a valid scientific question. But alternatives must explain the evidence. They must match orbital motions, compactness, accretion behavior, gravitational wave signals, shadow sizes, and the absence of a surface where one would create observable effects. This is a good module for mature skepticism. Science does not say black hole because the phrase is dramatic. It says black hole when the mass, size, behavior, and observations make other explanations weak. The strength of the claim comes from surviving comparison. Return once more to the bright ring around Messier 87 star. Its value is not only emotional. The ring size and shape can be compared with predictions from models of black holes and accretion flows. If the observed structure had been wildly inconsistent with general relativity, it would have opened a major problem. Instead, the image fit the broad expectations for a supermassive black hole. This is why careful images matter. They are not posters. They are measurements. The beauty comes from the fact that the same ring can inspire wonder and test physics. The dark center is not only mysterious, it is quantitative. Sagittarius. A star is the center of our galaxy, but it is not currently blazing like a quasar. It accretes relatively weakly compared with the most active galactic nuclei. This contrast helps the listener understand black holes as systems with changing environments. The same basic object can be quiet or active depending on how much gas is available, how it flows, and how the surrounding galaxy feeds the center. The Milky Way's black hole is therefore not a cosmic lighthouse today. It is more like a quiet engine with the capacity for activity. Other galaxies show what happens when central black holes feed more vigorously. The darkness is not always equally dramatic. At the largest scales, black holes are part of galaxy evolution. They do not create the cosmic web by themselves, but they participate in the life of galaxies that live within it. Supermassive black holes grow through accretion and mergers. Galaxies merge. Gas falls inward. Star formation rises and fades. Feedback from active galactic nuclei can heat gas and change future growth. This module broadens the black hole story without making unsupported claims. Black holes are not isolated curiosities. They are woven into the history of galaxies. A horizon may be local, but the consequences of feeding and feedback can echo through structures far larger than the black hole itself. People often ask which black hole is closest to Earth. This is exactly the kind of claim that needs caution, because candidate lists change as observations improve. Some nearby candidates have been revised or disputed. Others have been identified through stellar motion, binary behavior, or other indirect evidence. The safe documentary approach is to avoid building the script around a fragile record holder unless it is freshly verified during production. The useful discovery is broader. nearby black holes can be difficult to confirm. Distance alone is not enough. Astronomers need mass estimates, compactness, orbital data, and checks against alternative explanations. The nearest black hole is not just a fact. It is a measurement problem. The Milky Way likely contains many stellar mass black holes because many massive stars have lived and died across its history. But this does not mean black holes are sprinkled beside every star or waiting near every planet. Space is vast. Even a large population can be thinly distributed across a galaxy. Most black holes are not close enough to affect Earth. The fear of a nearby black hole swallowing the solar system is not supported by ordinary galactic conditions. This correction keeps the wonder calm. Black holes are real and numerous enough to matter for astronomy, but the universe is not a trap filled with hidden drains. It is mostly distance, motion, and time. Imagine an astronaut falling toward a large black hole in an idealized thought experiment. From the astronaut's own perspective, crossing the horizon may not be marked by a sudden flash or wall. Their clock continues. Their local physics remains locally normal at the crossing. From far away, however, signals from the astronaut become delayed, redshifted, and harder to receive. The outside observer never sees a simple live crossing in ordinary light. This is one of the most powerful relativity modules because it turns a familiar question into a viewpoint lesson. What happens depends on who measures it. Black holes force the script to separate local experience from distant observation. Outside the horizon, black holes are increasingly well measured. We can track stars, image shadows, detect mergers, and study disks and jets. Inside the horizon, direct astronomy stops. This does not mean scientists know nothing. General relativity gives a mathematical description. Quantum gravity research explores possible deeper answers, but no signal from inside the horizon returns to telescopes. The boundary is therefore not only physical, it is epistemic. It marks a limit on what the outside universe can be told. A black hole is a place where knowledge itself has a horizon. At the end of the journey, the black hole is no longer just a dark circle. It is a family of evidence. At Cygnus X1, the evidence is motion and X-rays. At Sagittarius, a star, it is stellar orbits and a shadow image. At Messier 87, it is a ring, a jet, and a galactic engine. At LIGO, Virgo, and Cagra, it is gravitational waves. In microlensing, it is background starlight briefly reshaped by an unseen mass. Each destination adds a different way of knowing. The black hole itself may hide its surface, if surface is even the right word. But the universe around it keeps giving testimony. Stars move. Gas shines. Light bends. Space-time rings. Return to the idea of a black hole with a companion star. In an X-ray binary, the black hole can pull gas from the companion into a hot accretion flow. The gas heats so intensely that it emits X-rays. This gives astronomers a practical clue. A dark, compact object may be hard to see, but the stolen gas can become a beacon. The system is not bright because the black hole has a glowing surface. It is bright because matter is losing gravitational energy before disappearing from view. This is one reason binary systems are so important. They make invisible objects measurable. The companion star provides motion. The accretion flow provides radiation. Together, they turn a hidden remnant into an astrophysical laboratory. Some black hole binary systems are not steadily bright. They can spend long periods in a quieter state, then erupt when conditions in the accretion disk change. During an outburst, X-ray brightness can rise dramatically. This gives the listener another kind of travel, not only through space, but through behavior. A system can appear faint, then become an intense X-ray source when stored material suddenly moves inward more efficiently. The black hole itself has not awakened in a conscious sense. The surrounding disk has changed state. Material that was orbiting and waiting becomes unstable, heats, and radiates. The darkness at the center remains dark, but the environment announces a new phase. Near a black hole, not every circular orbit is stable. There is an innermost stable circular orbit, often shortened to ISCO in technical writing. Inside that region, matter can no longer maintain a stable circular path in the same way. This matters because the inner edge of an accretion disk helps shape the radiation we observe. Around rotating black holes, the location of this inner stable orbit depends on spin and direction of orbit. The idea is precise but visual. Imagine a disk narrowing inward until ordinary circular motion loses its footing. The gas does not hit a surface. It crosses a boundary in orbital possibility, moving from long-lived circling into a more final inward plunge. The hottest regions near stellar mass black holes often shine in X-rays. Around supermassive black holes, X-ray emission can also come from energetic regions close to the disk, sometimes called a corona. Those X-rays can be shaped by strong gravity, high speeds, and hot plasma. Spectral features may be broadened or shifted by motion and gravitational effects. The details are complex, but the basic lesson is clear. Light near a black hole carries information about the environment that produced it. This makes X-ray astronomy one of the essential black hole tools. The visible eye sees darkness. X-ray telescopes can see violence around the dark center. A black hole becomes a physics experiment written in high-energy light. Some black holes are most dramatic in radio wavelengths. Jets and lobes can glow far from the central engine, tracing particles and magnetic fields over enormous distances. Centaurus A is a famous nearby active galaxy with prominent radio structures. Messier 87 has its own powerful jet. These systems remind us that the black hole's influence is not confined to the horizon. Radio astronomy turns invisible engines into extended maps. The central black hole may be tiny compared with the whole structure, but the jet marks where energy has traveled. A dark object can write enormous signatures across the sky, not by shining from its surface, but by organizing matter and fields around it. Now imagine a galaxy cluster, a city of galaxies embedded in extremely hot gas. At the center of the Perseus cluster, the active galaxy NGC 1275 hosts a supermassive black hole whose activity has helped carve cavities in the surrounding gas. This is one of the clearest ways to visualize feedback. Jets from the central engine can inflate bubbles and stir the cluster environment. The black hole is not acting alone by gravity. It is affecting gas through energy released by accretion. The scale is extraordinary. A horizon belongs to a central compact object, but its feeding episodes can leave marks across cluster gas. The destination has changed from a single star to an entire cluster atmosphere. Galaxies do not always live alone. They pass, distort, and sometimes merge. When galaxies interact, gas can be disturbed and driven inward towards central regions. This inward flow can feed supermassive black holes and trigger active galactic nuclei. It can also bring two central black holes into the same newly merged galaxy. Over time, those black holes may sink toward the center and form a binary. This module connects black holes to galactic history. A merger is not only a collision of stars. It is a rearrangement of gas, gravity, and central engines. The black hole becomes part of a larger choreography in which galaxies reshape each other's futures. The Milky Way and Andromeda are moving toward a future interaction on cosmic timescales. Both galaxies are expected to host central supermassive black holes. When the galaxies merge, their central regions will eventually become part of a new system. This does not mean stars will collide like grains of sand in a box. Galaxies are mostly empty space. The transformation is gravitational, structural, and gaseous. Orbits change. Gas can be compressed or displaced. Central black holes may eventually become a pair. This is a useful future-facing destination because it places black hole evolution inside our own cosmic neighborhood. The dark center of the Milky Way is not frozen forever. It belongs to a galaxy with a future. When two black holes merge, gravitational waves can carry away momentum. If the emission is uneven, the remnant black hole can receive a recoil kick. In some cases, this kick may move the remnant relative to its original environment. The effect depends on masses, spins, and merger geometry. It is not a cartoon explosion. It is momentum conservation through gravitational radiation. This discovery adds motion after merger. The final black hole is not always born perfectly still at the center of everything. Strong gravity can produce a remnant with a new trajectory. Even after the horizons combine, the story can continue through the motion of the object left behind. A rotating black hole stores energy in its spin. Under certain conditions, energy can be extracted from the rotating spacetime and surrounding magnetic fields. In astrophysical discussions, this is often connected to powerful jets. The important caution is that the process is not a machine bolted to the horizon. It is a plasma and magnetic field problem in curved spacetime. The black hole's rotation can help power the system, but the environment matters. This gives the listener a deeper picture of jets. They are not simply exhaust from swallowed matter. They can be tied to the spin of the central black hole, the magnetic field structure, and the disk that feeds the engine. If black holes are described externally by mass and spin, then different observations should agree on those properties. Gravitational waves provide one way to test this. The in-spiral, merger, and ring-down should fit the behavior expected for black holes in general relativity. Future detectors may improve these tests. They could measure ring-downs more precisely, compare different parts of a waveform, and look for deviations from the expected pattern. The exciting part is not that the theory has already failed. It is that black holes give us a place to test it carefully. A dark merger becomes a measuring tool for the shape of gravity itself. Not every compact merger is two black holes. Sometimes a black hole may merge with a neutron star. This kind of event is different because the neutron star has matter outside a horizon. Depending on masses and spins, the neutron star may be swallowed whole or tidally disrupted before merger. If matter remains outside the black hole, there may be electromagnetic signals. If not, the event may be known mostly through gravitational waves. This distinction helps prevent a common flattening. Compact object mergers are not all the same. A black hole pair, a neutron star pair, and a neutron star black hole pair can each tell different stories about gravity, matter, and the behavior of dense objects. The famous neutron star merger observed in 2017 was not a black hole merger, but it matters for black hole storytelling. It showed how gravitational waves and light can work together in multi-messenger astronomy. When neutron stars merged, telescopes detected electromagnetic signals as well as gravitational waves. That event helped connect compact object mergers to heavy element production and kilonova light. For black holes, the lesson is contrast. Binary black hole mergers often produce no confirmed light because there may be little matter outside the horizons. Neutron star events can be brighter in ordinary astronomy because matter is involved. The difference teaches what a horizon removes from the scene. Some black hole candidates are found by watching the motion of ordinary-looking stars. If a visible star wobbles or orbits around an unseen companion, astronomers can estimate the hidden object's mass. This method requires caution. A dark companion could be a faint star, a white dwarf, a neutron star, or a black hole depending on mass and compactness. The evidence must rule out less extreme possibilities. The scene is quietly dramatic. A star in the sky may look ordinary, but its motion can betray an invisible partner. Black holes are not always found by bright disks or violent mergers. Sometimes they are discovered by the patience of measuring a star's path. The center of the Milky Way is not easy to study in visible light because dust blocks much of the view. Infrared and radio observations are essential for seeing through the obscuring material. This gives the episode a practical observational lesson. The universe does not reveal every structure in the same wavelength. To study Sagittarius, a star and its surrounding stars, astronomers need the right kind of light. The galactic center becomes a destination hidden behind a veil. Ordinary vision fails, but infrared cameras, radio arrays, and careful long-term monitoring open the path. The black hole is not merely distant. It is concealed by the material of our own galaxy. Astronomers weigh black holes by measuring effects on nearby matter and light. In binaries, companion motion can reveal mass. In galactic centers, stellar or gas orbits can reveal central mass. In mergers, gravitational waves encode the masses of the objects involved. There is no cosmic scale under the black hole. The weighing is indirect but powerful. It depends on dynamics, light, models, and repeated measurement. This module helps the listener trust the evidence. A black hole's mass is not guessed because the object looks mysterious. It is inferred because its surroundings move in ways that can be measured. Gravity becomes the scale. Astronomers have found relationships between supermassive black holes and properties of their host galaxies, especially the central bulge of stars. These relationships suggest that black hole growth and galaxy evolution are connected. The connection is not a simple one-way command. A black hole does not personally arrange every star in the galaxy. Instead, gas inflow, star formation, mergers, and feedback shape both the central black hole and the surrounding galaxy over time. The useful claim is balanced. Black holes and galaxies grow together in linked histories. The details are still studied, but the pattern is too important to ignore. The dark center is part of the galaxy's biography. Compare the Milky Way with a bright quasar. Both can contain supermassive black holes, but their appearances differ enormously. The difference is feeding. An active galactic nucleus requires available gas falling into the central region. If little gas reaches the black hole, the center may be quiet. If gas flows inward efficiently, the same kind of central object can power tremendous emission. This comparison gives the listener a clear rule. Black hole brightness is environmental. A quiet black hole is not weaker in its basic identity. It is less supplied. The horizon defines the object, but the surrounding fuel determines the show. Matter falling into a black hole can convert a significant fraction of its rest mass energy into radiation before crossing the horizon, especially in efficient accretion disks around compact objects. This is why quasars can be so luminous. Nuclear fusion in stars converts only a small fraction of mass into energy. Accretion onto black holes can be an extremely efficient engine under the right conditions. The comparison should be used carefully. A black hole is not burning fuel like a star. The energy comes from gravity and orbital motion as matter moves inward. The light is released outside the horizon. The darkness powers brilliance by making the fall deep. When astronomers map the sky in X-rays and gamma rays, compact objects and active galaxies become important. Black holes are part of the high-energy universe because they create extreme conditions around them. Hot disks, jets, coronae, and tidal disruption events can all produce radiation far beyond visible light. A calm night sky hides a violent multi-wavelength sky. This module broadens the sensory field. The human eye sees stars. Radio telescopes see jets. X-ray telescopes see hot inner flows. Gravitational wave detectors sense mergers. Black holes are not one kind of darkness. They are crossroads where many messengers become necessary. Black holes are often described as places where physics breaks. That phrase can be misleading. Outside the horizon, physics works well enough to make precise predictions. General relativity describes orbits, lensing, time dilation, waves, and shadows with remarkable success. The unknowns appear at deeper boundaries. The singularity predicted by classical theory, the information problem, and the need to connect gravity with quantum mechanics. So a safer statement is this: black holes do not destroy physics. They reveal where our current theories are powerful and where they may be incomplete. They are not the end of science. They are one of science's most demanding test sites. General relativity raises the possibility of singularities, but many physicists have considered whether nature hides them behind horizons. This idea is associated with cosmic censorship, though the full question is technical and not fully settled. For a documentary, the useful point is careful and modest. Observed black hole candidates are understood as objects with horizons or horizon-like behavior, while naked singularities are not established astronomical objects. This module belongs in the frontier section, not the observational core. It shows how black holes lead from measured astronomy into deep mathematical questions. The script should label the boundary clearly. This is about theory, not a photographed object. Black holes have entropy proportional to the area of the horizon, not the volume inside. This is one of the strangest and most important results in theoretical physics. Entropy usually measures the number of microscopic ways a system can be arranged. For black holes, the relationship to horizon area suggests a deep connection between gravity, information, and the structure of spacetime. This is not an easy visual module, but it is worth including because it changes the meaning of a horizon. The boundary is not only the point of no return. In theory, it carries thermodynamic meaning. Darkness becomes a clue to information. Current ground-based detectors are sensitive to certain ranges of gravitational waves, especially from stellar mass compact object mergers. ESA's planned LISA mission would listen from space at lower frequencies. That kind of space-based detector could observe massive black hole binaries that ground detectors cannot hear in the same way. It could also follow longer in-spirals and different kinds of sources. This gives the ending a forward path. Black hole astronomy is not finished. The next instruments may add new destinations to the map: heavier binaries, earlier in spirals, and signals from galactic centers. The universe has already spoken through space-time. We are still building better ears. The fullest black hole picture does not come from one method. It comes from combining messengers. Radio images show shadows and jets. Infrared observations track stars near the Milky Way center. X-rays reveal hot accretion. Optical surveys catch flares. Gravitational waves measure mergers. Each messenger has blind spots. Light struggles to show the horizon directly. Gravitational waves may provide little sky detail without a network. Accretion tells us about surrounding gas, not the horizon alone. Together they create a stronger portrait. The black hole remains hidden in one sense, but not unknowable. It is approached through many doors, each opening onto a different kind of evidence. At the beginning, a black hole may have seemed like one destination, a dark point in space. Now the map has expanded. There is Cygnus X1, where a companion star helped reveal a hidden compact object. There is Sagittarius, a star where stars orbit the Milky Way's central mass. There is Messier 87 with its shadow and jet. There are LIGO, Virgo, and Cagra, where space-time waves are measured on Earth. There are quasars, clusters, binaries, micro-lensing events, globular clusters, and future detectors. This is exactly why recognizable destinations matter. They turn a concept into travel. The listener is no longer only hearing about black holes. They have moved through the evidence. A black hole can feed only through its surroundings, and intense radiation can push back on infalling gas. The Eddington limit describes a balance between inward gravity and outward radiation pressure for ionized gas under idealized assumptions. This does not mean no black hole can ever appear brighter than a simple Eddington estimate. Geometry, beaming, opacity, and accretion physics can complicate the picture. But the idea gives astronomers a useful scale. For the listener, it changes the image of feeding. Matter does not simply pour inward without resistance. Light itself can push. A black hole's meal can become self-regulating, with gravity pulling gas down while radiation fights its way outward. The early universe contains quasars powered by very massive black holes, and that raises a growth problem. To grow quickly, a black hole needs a seed, a supply of gas, and conditions that allow rapid accretion. Small seeds from early stars might grow if they feed efficiently for long enough. Heavier seeds from direct gas collapse could begin closer to the required mass. Mergers may also contribute. This is not a settled origin story. It is an active research puzzle. The safe wonder is that supermassive black holes existed early enough to challenge simple growth pictures. Their presence does not break cosmology, but it pushes models to explain how the first giant engines formed. Some off-center X-ray sources in other galaxies shine brighter than ordinary stellar systems would seem to allow. These are called ultraluminous X-ray sources, or ULX sources. Some may involve stellar mass compact objects accreting in unusual ways. Some have been identified as neutron stars after pulsations were detected. Others have been discussed as possible intermediate mass black hole candidates. The category is valuable precisely because it is mixed and challenging. This is another caution module. A bright X-ray source is not automatically a black hole and not automatically an intermediate mass black hole. The evidence must identify the compact object, the accretion geometry, and the true luminosity. Brightness opens the question. Timing, spectra, pulsations surrounding gas, and careful modeling are what begin to close it. Astronomers discuss possible mass gaps among compact remnants. One gap concerns the boundary between the heaviest neutron stars and the lightest black holes. Another concerns black holes that may be difficult to form through ordinary stellar collapse because of pair instability processes in very massive stars. Gravitational wave detections have made these questions more active. Some events appear to involve masses that challenge older simple categories. This is a strong place for careful wording. A mass gap is not a law painted onto the universe. It is a pattern or predicted region that observations can test and revise. Black holes keep turning classification into discovery. In very massive stars, high-energy photons can create electron-positron pairs under extreme conditions. This can reduce pressure support and trigger violent instability. Depending on mass, the star may pulse and shed material, or it may be completely disrupted in a pair instability supernova, leaving no black hole remnant. At still higher masses, other outcomes may become possible. This module helps explain why black hole masses are not arbitrary. Stellar physics shapes which remnants can form. A black hole's mass carries a history of nuclear burning, winds, metallicity, collapse, and explosion. When LIGO detects a heavy black hole, it is also giving clues about the star or merger history that produced it. The chemical composition of a massive star affects how much mass it loses through stellar winds. Stars with fewer heavy elements can retain more mass before collapse, which may help produce heavier stellar mass black holes. This connects black holes to cosmic history. Early generations of stars often formed in environments with fewer heavy elements than the present-day Sun. Their winds and final remnants may have differed from those of similar stars in richer environments. The destination here is not one named black hole, but a stellar nursery in a different chemical era. The final remnant depends on the star's life, and the star's life depends partly on what the surrounding universe was made of when it formed. In crowded star clusters, compact objects can meet, exchange partners, and form binaries through gravitational encounters. A black hole binary formed this way may have a different history from one born from two massive stars that evolved together. This matters for gravitational waves. The spin directions, masses, and orbital properties of merging black holes can carry hints about how the pair formed. There are two broad routes to imagine. One is isolated binary evolution, where two stars live and die together. Another is dynamical assembly, where black holes meet inside a dense cluster. The merger signal may help tell which path nature used. A gravitational wave signal is not just a detection beep. Its changing frequency and amplitude carry information. The Earlian spiral gives mass and orbital clues. The merger probes the strongest gravity. The ringdown reveals the final black hole settling. In this sense, the waveform is a fossil of motion. It records a history that no telescope may have seen in light. The listener can imagine the signal as a rising tone, but the science is more exact than sound. Detectors measure changes in length. Computers compare the signal with models. The final result is a reconstruction of two dark objects moving through space-time. After two black holes merge, the new horizon is distorted. It settles into a stable shape by emitting gravitational waves. This final phase is called ringdown. The name is helpful because it resembles a struck bell settling after a note, but the analogy has limits. A black hole is not metal vibrating in air. It is curved space-time relaxing through gravitational radiation. Ringdown matters because its frequency should depend on the final black hole's mass and spin. If future observations measure ringdown in greater detail, they can test whether the remnant behaves like the black holes predicted by general relativity. For a brief moment during merger, the power emitted in gravitational waves can be enormous. This does not mean the event is bright, invisible light. It means energy is being radiated through space-time itself. The phrase can sound exaggerated, so the script should explain it carefully. The luminosity is in gravitational waves, not ordinary light. a binary black hole merger may be optically dark while still releasing tremendous energy in ripples of geometry. This module gives the listener an almost paradoxical image. One of the most powerful events in the universe can happen in darkness. The universe does not need a flash to be violent. When black hole mergers are detected without clear electromagnetic counterparts, that absence can be meaningful. It suggests there may have been little matter outside the horizons to heat, collide, or glow. Absence is not proof by itself. Telescopes may miss faint or poorly located signals, but the lack of light fits the expectation for many binary black hole mergers. This is a quiet science lesson. Evidence is not only what appears, it is also what fails to appear when a theory predicts little should be visible. In black hole astronomy, darkness is not ignored. It is interpreted with care. Light has polarization, a direction associated with its electromagnetic wave. Around black holes, polarization can help trace magnetic fields in the emitting plasma. Event horizon. Telescope polarization studies of Messier 87 star in Sagittarius. A star add another layer to the shadow images. They do not merely ask where the ring is bright. They ask how the light is oriented, which helps probe magnetic structure near the black hole. This gives the listener a refined destination. First, we saw a ring. Then we asked what the ring's light was doing. The black hole image becomes not only a silhouette, but a map of magnetized plasma near a horizon. Magnetic fields near black holes can shape disks, launch jets, move angular momentum, and help control how gas falls inward. Without magnetic fields, many accretion processes would be difficult to explain. This is important because popular images often show glowing disks as if they are simple whirlpools. Real accretion flows are plasma systems. Charged particles, turbulence, radiation, and magnetic fields all matter. The destination is now inside the disk itself. The listener is not just seeing a bright ring from far away. They are imagining a living plasma, threaded by invisible lines of force, converting orbital energy into heat and sometimes channeling power into jets. Gas does not fall into a black hole just because gravity exists. If the gas has angular momentum, it tends to orbit. To move inward, it must lose some of that angular momentum. Accretion disks are therefore not simple drains. They are systems that transport angular momentum outward while allowing some matter to drift inward. Turbulence and magnetic effects help make this possible. This corrects the mental image again. A black hole does not simply swallow everything nearby. Matter has motion. Motion resists direct collapse. The path inward is a negotiation between gravity, rotation, heat, pressure, and magnetic fields. Tidal disruption connects to a broader idea. When gravity differs strongly across an object, the object can be pulled apart. Around planets, this idea appears in discussions of moons and rings. Around black holes, it becomes far more extreme. A star passing close to a supermassive black hole can cross a tidal boundary where its own gravity can no longer hold it together. The star stretches into streams, and some material may later form an accretion flow. This gives a useful bridge from familiar solar system dynamics to black hole violence. The physics of tides is not invented at the horizon. It is the same principle carried into a deeper gravitational field. After a tidal disruption, the star's debris does not all vanish at once. Some material may escape. Some remains bound and returns toward the black hole. As returning streams collide and circularize, they can create a bright, temporary accretion event. This makes tidal disruption a time-dependent scene. The discovery is not only the moment the star is torn apart, it is the aftermath. Streams, shocks, heating, radiation, and gradual fading. The black hole again remains dark at the center. The visible story is written by matter outside the horizon, trying to find new paths after the star's original structure has been destroyed. An active black hole may not stay active forever. If the gas supply weakens, the accretion flow can fade. A galactic nucleus that once shone brightly may become much quieter. This changes the sense of cosmic time. A black hole is not permanently a quasar or permanently silent by identity. Its appearance depends on what reaches it. The Milky Way center may preserve hints of past activity in surrounding structures, while other galaxies show far more active states today. The central engine can have episodes. A black hole's life is not just formation and final darkness. It can have feeding seasons across cosmic time. Quasars can act as background lamps. Their light passes through gas between galaxies on the way to Earth, leaving absorption features that reveal material otherwise hard to see. In this role, a black hole-powered object becomes a probe of the universe beyond itself. The quasar shines because of accretion near a supermassive black hole, but its light also maps intervening gas across cosmic distances. This is a beautiful inversion. A black hole's environment produces light, and that light teaches us about matter nowhere near the black hole. The dark engine helps illuminate the cosmic web. When astronomers observe distant quasars, they are looking back in time. The light began its journey when the universe was younger. The black hole powering the quasar is therefore not only an object, but a historical marker. This makes black holes useful for cosmic archaeology. Their masses, luminosities, host galaxies, and environments help reconstruct how early structures formed and grew. The listener can imagine each distant quasar as a lamp from an earlier chapter of the universe. The black hole at its center is not just consuming matter. It is preserving evidence of a time when galaxies, gas, and central engines were still rapidly changing. Not every supermassive black hole is actively feeding. Many galaxies may host central black holes that are quiet today. Their presence can be inferred through stellar or gas dynamics, but they may not shine as active galactic nuclei. This is similar to the stellar mass case at a grander scale. A black hole's visibility depends on environment. Without enough infalling material, even a giant may be dim. This gives the cosmic map a hidden layer. Bright quasars are spectacular, but they are not the whole population. Behind the active lights may be many quiet central masses waiting at galactic centers, known mainly through gravity. Because light takes time to travel, every distant black hole system is seen in the past. Messier 87 is seen as it was millions of years ago. Distant quasars are seen as they were billions of years ago. This does not make the observations less real. It is how astronomy works. Looking outward is also looking backward. For a black hole documentary, this becomes a structural gift. The journey can move from the Milky Way center to nearby active galaxies to ancient quasars, and each step changes not only location but epoch. Black holes become markers along the timeline of the universe. Several words around black holes are useful but dangerous. Singularity is not an observed object. Shadow is not the event horizon itself. Jet is not matter escaping from inside the horizon. Evaporation is not something observed for stellar black holes. Wormhole is not a confirmed travel route. This module is not a retreat from wonder. It is what keeps the wonder honest. The more extreme the topic becomes, the more careful the language must be. Black holes are already extraordinary when described accurately. They do not need exaggerated shortcuts. Precision makes them stranger, not smaller. No single imagined spacecraft can carry the whole episode. Sometimes the best viewpoint is near a safe orbit. Sometimes it is Earth, with radio dishes spread across continents. Sometimes it is a star moving around Sagittarius, a star. Sometimes it is a detector arm stretching through a quiet landscape. This is the practical writing lesson from the new protocol. Black holes are not one scene. They are a network of scenes connected by gravity. The listener should feel movement, from horizon to star, from galaxy center to detector, from X-rays to radio, from theory to observation. The voice remains calm, but the attention keeps traveling. The final discovery before the closing is that black holes have turned darkness into a map. Each method draws a different line. Stellar orbits map mass. X-rays map hot gas. Radio images map plasma near horizons. Jets map magnetic power. Gravitational waves map mergers. Microlensing maps hidden compact objects. Quasars map early galaxies and intervening gas. The black hole itself still hides its interior. That limit remains. But around the limit, astronomy has built a geography of evidence. The destination is dark, yet the route toward it is filled with signs. Now imagine the journey widening one last time. The Milky Way turns slowly around its quiet central darkness. Messier 87 sends a jet across intergalactic space. Somewhere in the distant universe, two black holes complete their final orbit and a ripple begins its long journey toward Earth. Somewhere else, a dark remnant passes silently in front of a background star, borrowing that star's light for a moment so it can be known. Black holes are often described by what they take away: light, escape, information, certainty. But astronomy has learned to know them through what remains outside: the path of a star, the heat of a disk, the curve of a photon, the shape of a shadow, the tremble of space-time after a merger. They are not empty holes in a painted sky. They are places where gravity becomes strong enough to reveal the deep rules of the universe. They connect the deaths of stars to the growth of galaxies, the quiet center of the Milky Way to detectors on Earth. and the edge of known physics to the oldest questions about space, time, and information. And as Hypnos guides us back from those dark centers, the ordinary night feels a little larger. Above us, the sky is not only filled with stars, it is filled with hidden structures, invisible motions, and silent evidence. Even darkness has a shape. Even absence can teach. And in the deep universe, the things we cannot see directly may still be among the most powerful guides to what reality is.